Welcome back to the 3 months of Modal Logic, the sequel to 100 Days of Logic here with Carneades.org. Today we are looking at the final video in the 3 months of Modal Logic, video number 200 in this gigantic series on logic, and we are going to be looking at, in this video, 10 perplexing puzzles for the master modal logician, putting your modal logic skills to the test. Now, these puzzles are not just going to be for alephic modal logic, they are going to be for all of the different kinds of modal logic that we have studied, at least the big main types of modal logic that we have studied, and hopefully they're going to highlight some of the interesting differences and implications of which axioms and rules are chosen for which logic. In this video, we're going to have both the puzzles and the solutions. So if you want to try the puzzles, please pause the video in the middle, try them on your own, and then jump to the end or jump to the second half of the video for all of the answers. Okay? So, for all of the following problems, remember that Axiom K works like this. Necessity can go into an implication. It can be distributed across an implication. If it's necessary that P implies Q, then if it's necessary that P, it is necessary that Q. It does not work like this. If you have a negation outside that necessity, you can't still distribute the necessity inside of your parentheses. That is important because that's kind of a quick shortcut that you can use, but your proofs are not going to be valid if that's what you use. Okay? There's other ways to do it, so try to work around that problem. With that said, so the first 6 puzzles are going to resemble Axiom K in their form. They will all require both Axiom K and the necessitation rule. If you can prove any of these without the necessitation rule, or without Axiom K for that matter, please show me how in the comments below. I have not yet found a way to prove any of them without these 2 axioms. You can also use the definitions of these terms. For example, it's permissible that P equals. It's not the case that it's obligatory that not P, and so on and so forth. For these first problems, do not use the MDist, or the modal distribution rules that were shown in the Modal Logic's Basics video, because a lot of these are going to actually be the same as those MDist rules. And in fact, most of these puzzles are going to be showing you how to prove those rules. So, don't use them because then you can just declare that rule and say it's proved. But if you can prove any one of those rules, you're welcome to use it. It should be noted that there are cases against the necessitation rule in epistemic and deontic logic, and a pretty convincing one in epistemic logic. However, as noted, that it is very difficult to actually prove things without the necessitation rule. And this is one of the things I really want to demonstrate here. It is very, very difficult to prove very intuitive axioms if you don't have the necessitation rule included in your logic. Even though I've made cases against it, here's one of the reasons that logicians want to fight to keep it in. All of these intuitive consequences of Axiom K require the necessitation rule. So, even though it might not make sense that all of the laws of logic are obligatory, if we don't make it that way, there's a lot of things in deontic logic that we can't do. And the same is going to apply for all of our modal logics. So, for these, I will allow you to use the necessitation rule even in epistemic and deontic logic, even though it really arguably doesn't make sense for epistemic logic, and there is an argument to be made for it not making sense in deontic logic. Okay? With all of those preliminaries out of the way, let's get started. So, your first puzzle is to prove, once again, this should look very similar to Axiom K. Instead of distributing our strong operator across implication, we're exporting our strong operator. We're bringing it outside the brackets across disjunction, and we're doing it with knowledge. So S knows that P or S knows that Q implies that S knows that P or Q. And your next job after that is to prove that if it's permissible that P and Q, that implies that it's permissible that P and it's permissible that Q. Remember, once you've proven any one of these rules, so if you prove one, for example, that's going to hold for any modal logic system that has both Axiom K and the necessitation rule. So you can then use that axiom in the different forms with the different strong operators, it doesn't just have to be knowledge, in your future proofs. Okay? Hopefully that makes sense. For the following, assume only minimal temporal logic, K, GP, HF, and the necessitation rule. And though we did not state it explicitly in the original video, you can help yourself to the change of temporal quantifier rule, which makes sense with all of the change of quantifier rules. It should perfectly map onto all of them. These correspond to the modal distribution rules shown in the modal logic video. Once again, do not use those rules until you have proved them first from Axiom K and the necessitation rule. But if you've proven them in deontic or epistemic logic from the previous two problems, then you're welcome to use those here as well. So your first task is to prove if it has always been the case that P and Q, then it has always been the case that P, and it has always been the case that Q. And then you need to prove at some point in the future, it will be the case that either P or Q implies that at some point in the future it will be the case that P, or at some point in the future it will be the case that Q. Okay? Those are your next two challenges to prove. And finally, for this puzzle, Axiom K and the necessitation rule should be sufficient. And try to only use any version of modal distribution you've already proven from Axiom K. And I will tell you that there is a faster way than the longer version if you use one of the modal distribution rules you've already proven. Now, there are 12 possible iterations of Axiom K which differ in three factors: the operation, either disjunction, conjunction, or implication; the modal operator, either strong or weak; and the direction, either distribution or exportation. 3 times 2 times 2 equals 12, so there's 12 possible combinations of those three factors. For example, the original Axiom K distributes the strong operator over implication, while the problem below, that you're about to see in a second, exports the strong operator over conjunction. Once you have solved this puzzle, exporting the strong operator over conjunction, you will have proven 5 of the 12 iterations of Axiom K. One of these iterations we proved in the original video on the modal logic basics. That was exporting the weak operator over implication. And counting the axiom itself, distributing the strong operator over implication, that gives us 7 iterations either proven or assumed. Of the remaining 5, it seems to me that only one of them can actually be proven, though I'm not sure if there's some way to demonstrate that the other 4 can be disproven, if there's a way to actually prove them, or if there's a way to demonstrate that they can neither be proven nor disproven. For the 6th challenge, try to figure out which of the remaining 5 iterations can be proven, and then go ahead and prove it. For an even greater challenge that we're not going to show the answer to, either prove that the 4 final iterations are false, or cannot be proven to be true or false, or, though it seems to me they can't be, demonstrate them to be true. All right? Hopefully that makes sense. Hopefully it makes sense what I'm saying here about the different iterations, which of the iterations you're trying to find, and how you can prove it. Okay? Give those a try. So, number 6, find and prove the final valid iteration of Axiom K. Okay? So, for the next 4 problems, we're going to shift gears a little bit from kind of all of the iterations of Axiom K to looking at some translations. So, for the last 4 problems, you'll first need to translate statements into modal logic, and then prove them. I would highly encourage you to practice this because this is an important piece of modal logic, which is how you can represent real-world statements in modal logic. If you just want to practice the logic, you can jump ahead to the answers and then pause the video before I show the proof and just look at the premises. Your job is to use the premises to prove the stated conclusion, not to assess the truth of the premises or the soundness of the arguments, only the validity. So, just because you may disagree with some of the premises doesn't give you the right to stop doing the argument altogether. The reason we have these arguments here is to check and see if they are valid, and to prove them valid, not to debate whether or not they're sound or the premises are true. Your goal is to try to solve them with as few axioms as possible, or as few commitments as you can have as possible. If you have to have more than a couple axioms, you may need that in some cases, but see how few axioms you can use to prove them. So, problem number 7. It is obligatory that you believe that God exists. There exists no reason that justifies belief in God. If you know something, there is some reason that justifies your knowledge. Therefore, that's our conclusion, which you're trying to prove. Therefore, there is something that you are obligated to believe which you do not know. Okay? The next problem. For all Muslims, it is obligatory, if you have not been on the Hajj in the past, that you go at some point in the future, and that you stone the devil when there. All Sunnis are Muslims. Rohan knows that Bill is a Sunni, and that he has never been on the Hajj, him being Bill. Therefore, it is obligatory that Bill go on the Hajj at some point in the future. It might be worthwhile for this problem at least to review the final 10 days of the original 100 days of logic and remember some of your predicate calculus skills there. Next up, number 9, murder is impermissible in all possible worlds. In all possible worlds, it is permissible to either be a vegetarian or commit murder. Therefore, in all possible worlds, it is permissible to be a vegetarian. It's important to remember in this the way that Axiom K works and the way that Axiom K does not work. Check the beginning of the video if you're curious. And finally, problem number 10. Fatu knows that she should have talked to her daughter about sex last week. Fatu knows that she has never before talked to her daughter about sex. Fatu knows that if she had an obligation at some point in the past and that obligation was not fulfilled at that point in the past, then she will have that obligation again at some point in the future. Therefore, Fatu will be obligated to talk to her daughter about sex at some point in the future. Okay? Give that problem a try, and then for an extra special bonus problem, solve the same problem, but imagine that Fatu is logically omniscient, or in other words, you can use the necessitation rule for epistemic logic, and the conclusion is that Fatu knows that she will have to talk to her daughter about sex at some point in the future, not just that she is obligated to talk to her daughter about sex at some point in the future. It's the same conclusion, but just with the knowledge operator stuck out in front. Give all of those problems a try. I highly encourage you to take the time, work them out, do your best to solve them. Don't try to jump ahead to the answers if you don't have to. But if you solve the problems already, or you want to take a look at the answers, let's go. So, there are a number of different ways to solve these problems. We will try to vary the methods that we're using in this video for solving them as we go. Offer questions below if you want to find out if your particular method is correct. All right? So, our first problem was S knows that P or S knows that Q implies that S knows that P or Q. The first thing we're going to do for this is an assumed conditional proof and just basically prove our addition rule that P implies P or Q, 1 to 2 conditional proof. Then we'll use the necessitation rule, because we noted at the beginning we're going to allow using the necessitation rule in epistemic logic, even though it's not standardly used. And then use Axiom K to distribute knowledge across P and P or Q. Then we're going to do another assumed conditional proof, draw our line going down, and prove basically the same rule. We could have also done this with kind of a universal instantiation of the addition rule in both of these cases. I just wanted to show you how it can be done with a conditional proof here. And then, once again, we'll use our necessitation rule and our axiom K to distribute knowledge across Q and Q or P. Then, if we want to conjoin our two results, we get either both S knows that Q implies that S knows that Q or P, and S knows that P implies that S knows that P or Q. We can then, using assumed conditional proof, assume the disjunction of the two antecedents of our implications in that conjunction in premise 11, and then use constructed dilemma and premises 11 and 12, correction there, to get S knows that P or Q. Therefore, 12 to 13, conditional proof, we get that S knows that P or S knows that Q implies that S knows that P or Q. Note that we've used the necessitation rule and axiom K and all of our other lovely rules of predicate calculus, but we haven't used any of our other modal logic axioms. None of these axioms can be proven in epistemic logic if we do not assume logical omniscience and therefore the necessitation rule. Even though it is not intuitive or justified in epistemic, deontic, or surely doxastic logic, without it, we can do very, very little. And that's one of the things that I want to emphasize and kind of underline as a takeaway from these problems here. If you don't have that necessitation rule, all of those modal logics become much, much weaker. All right? So, now any modal logic, which includes both axiom K and the necessitation rule, which, barring logical omniscience, epistemic logic doesn't actually include, can help itself to this axiom. We'll refer to this axiom and the others that we prove here, as we did in the first video on modal logic, as MDist, or modal distribution. So that's what the axiom looks like, or rather the consequence looks like, the rule looks like, and it's basically saying that we can export necessity out of a disjunction. All right? Or export any of the strong operators out of a disjunction. Okay? Now, problem 2. It's permissible that P and Q implies it's permissible that P and it's permissible that Q. In this one, we're going to take a little bit of a different tack. We're going to try an assumed indirect proof. So we're going to deny our conclusion, and that's our conclusion there, and hopefully we're going to end up with it at the end. So we deny our conclusion, we'll get through implication, De Morgan's law, and double negation, basically kind of distributing that negation through, we get both. It's permissible that P and Q, and it's not the case that it's permissible that P and permissible that Q. Those are 3 steps in one, but if you think about the way that an implication works, the only way that an implication can be false is if the antecedent is true and the conclusion is false. The consequent is false. So we'll simplify that down, just having the consequent there. We'll use De Morgan's law to distribute that negation, and then we'll use our deontic definitions to turn those permissibles into obligatories. Then using our newly found modal distribution rule, we'll take that obligation out, use De Morgan's law to pull out that negation, and our deontic definitions again to pull out the negation on the side of permissibility. Now, if we simplify premise 2, we can see that we have a contradiction, which was the goal of our indirect proof. So we can conjoin premises 8 and 9 to get a contradiction, and therefore conclude from 1 through 10 that indirect proof that you can distribute permissibility, or the weak operator, across a conjunction. Hopefully that makes sense. Once again, with all of these proofs, there's a number of different ways to do them. I'm trying to show you several different ways to do each of these kinds of proofs by doing each proof in a little bit of a different way. As before, this axiom will remain valid in any system with axiom K and the necessitation rule. The necessitation rule arguably does not make sense in deontic logic, but so much cannot be done without it. None of these great consequences that seem to make sense. It seems to make sense that if it's permissible that both P and Q, then it's permissible that P and it's permissible that Q. That makes sense. It's an intuitive conclusion. And yet, unless you can include the necessitation rule that anything which is a rule of logic is obligatory, you can't conclude that. You may say, well, wait, we didn't use the necessitation rule anywhere in this proof. Well, remember, we used our modal distribution rule, which was based on the necessitation rule. And so, unless we find some way to prove these things without the necessitation rule, then all of these will rely on it. Okay? Hopefully that makes sense. Moving on. The next problem was, if it has always been the case that P and Q, then it has always been the case that P, and it's always been the case that Q. So we're distributing the strong operator across conjunction. We'll start with an assumed conditional proof, assuming P and Q, drawing our line going down, and we'll simplify that P. Once again, you could have done a universal instantiation of simplification here, but I want to show the way to do it in conditional proof. We'll do another assumed conditional proof and do the same thing with Q. Both of these are just two different faces of simplification. Some people might say you have to do a commutativity in there. I'm not too concerned about it. Then, using temporal necessitation rule, we're going to, for both of those two statements in premise 3 and premise 6, have our "it has always been the case" stuck out front. Then we'll use an assumed conditional proof to assume the first half of our conclusion, that it has always been the case that P and Q. Then, using premise 7 and axiom K, we will conclude that this implies both it has always been the case that P and it's always been the case that Q. Therefore, using modus ponens, we can show that it's always been the case that P and it's always been the case that Q. Note that that second one should actually be premise 9 and premise 11, modus ponens. And therefore, we can conjoin them 12 and 13 to get it's always been the case that P and it's always been the case that Q. So, from premise 9 through 14, conditional proof, we have it's always been the case that P and Q implies it's always been the case that P and it's always been the case that Q. This rule, that we can distribute H, or the strong operator, across a conjunction will work for any modal logic that has both the necessitation rule and axiom K. So we can distribute necessity, obligation, knowledge, if you have logical omniscience, across a conjunction. I have not found a way to prove this rule without the necessitation rule, but if you have one, please offer it in the comments below, and we will subject it to some scrutiny. Next up, we have distributing possibility, or the weak operator, or it will at some point in the future be the case that, across disjunction. Once again, we're going to start with an assumed conditional proof and draw a line going down, but this time we're going to do a double assumed conditional proof, and we assume not P, and then we assume not Q. From 1 to conjunction, we can join not P and not Q. Therefore, we can show that not Q implies not P and not Q, which seems a little strange, but then you remember we are within an assumed conditional proof. Once we jump out of that, we get not P implies not Q implies not P and not Q. 1 through 4 conditional proof, which should make a little bit more sense. Then, once again, we have to use that necessitation rule. We'll use our necessitation rule to stick G out in the front. It should be the temporal necessitation rule, but necessitation rule will work for any of the necessitation rules really throughout our logics. Then we'll use our temporal axiom K to distribute G throughout that. And then, here's an interesting thing that we need to stop and take a look at. So, when you have G over another implication, so we have it will always be the case that not Q implies not P and not Q. It might be tempting to say we can just push that G into the implication, and technically we can, in that it's going to be true that G can be pushed in there. But because that's not exactly what axiom K says, we're going to do a little bit of a dance around it, and there's going to be a couple different ways we can do that. One of them we're going to show here, one of them we're going to show later in the video. So the first way we can do it is to universally instantiate Axiom K. So take Axiom K as for all P and all Q, and universally instantiate that P and Q to these two terms, basically saying that we have G over that implication implies G over the first part of the implication and G over the second part of the implication. And then use a hypothetical syllogism between 7 and 8 to get what we wanted to do anyway, which is push that G, which is distribute that G across that implication. So you can do it and you're allowed to do it, but to stay true to Axiom K, you might want to take that extra step. All right? So now we have G distributed across all of that. We'll use exportation to change the first part of that to a conjunction, transposition to switch them and throw some negations on, and then our change of temporal quantifier to switch those G's to F's. There's a lot of negations here right now, and it doesn't really look like what we're going for, but then a quick De Morgan's law and double negation will allow us to show that we can distribute the weak operator over disjunction. Distributing possibility, or the weak operator, across disjunction will follow directly from Axiom K and the necessitation rule. Note that we didn't use modal distribution in another way here. We just used Axiom K and the necessitation rule. Any system with both of these rules will include this as a consequence. But note that F is a weak operator, not a strong operator, so you would put in possibility or permissibility for F instead of necessity or obligation. Our next problem is exporting necessity across conjunction. So this is actually going to be really quick, as you can see by the size of it. We're going to first universally instantiate modal distribution. So one of the things that we proved earlier was that you could distribute possibility across a disjunction. It seems that if we think of disjunction and conjunction as opposites and necessity and possibility as opposites, that's doubly opposite the premise that we're trying to prove right now. And so you might think that this might be useful. So instead of instantiating these as P and Q, we're going to instantiate them as not P and not Q. Then we'll go ahead and use our change of modal quantifier rule to switch all those possibilities to necessities and add a number of negations in there. And then we'll get rid of those negations with a De Morgan's rule and double negation. We're almost there. A quick transposition will get rid of the negations and put everything in the right place to get us. It's necessary that P and it's necessary that Q implies that it's necessary that P and Q. This and our earlier proof show that we can both distribute the strong operator over conjunction and export the strong operator over conjunction, which means that it's necessary that P and it's necessary that Q is materially equivalent to it's necessary that P and Q. And that'll apply for any of the strong operators that include both Axiom K and the necessitation rule. Other iterations of Axiom K will be similarly paired so that the transposition of one is the statement of the other. Go ahead, try transposing some of them and see if you can prove some of these axioms in a simpler way. Not all of them are going to work that way, and you might prove something interesting that's not one of the axioms we're looking at here, or one of the propositions we're looking at here. Now, we're going to talk about the last iteration of Axiom K to be proven. So, before we can do that, let's take a look at all of the possible ways we can work through Axiom K. So, Axiom K originally is distributing necessity across implication. In the Modal Logic Basics video, at the end of the video, we showed how you can export possibility across implication. So both of those we know. The first one is assumed without argument, and it's an axiom. The second one we've shown how you can prove it. So far in this video, we've shown that you can export necessity across disjunction, distribute possibility across disjunction, distribute necessity across conjunction, export necessity across conjunction, and distribute possibility across conjunction. Left now, there are 5 different possible iterations of Axiom K. Let's take a look. Can we export necessity across implication? That would mean that it's necessary that P implies that it's necessary that Q implies that it's necessary that P implies Q. Well, that doesn't seem to make sense. So take, for example, that P is contingent. It's not necessary, but it's not impossible. So there's some possible worlds where P is true and some possible worlds where P is false. Then it is the case that it's necessary that P implies it's necessary that Q, because P is not necessary, and if the antecedent is false, then the whole implication must be true. However, that doesn't imply that it's necessary that P implies Q, because P is true in some possible worlds, and Q could be impossible for all we know. So it doesn't really work out. What about distributing possibility across implication? So we're saying it's possible that P implies Q. So in some possible world, in let's say one possible world, P implies Q, implies that it's possible that P implies that it's possible that Q. So let's say that one possible world, call it world A, has it true that P implies Q. And then some other possible world B, has it true that P is the case. It could be possible that Q is, in fact, impossible. Why? Because that could be the only world. World A could be the only world where P implies Q. And world B could be the only world where P is true. So you're never going to be able to get those two together to make a modus ponens. So that one's going to be invalid as well. What about distributing necessity across disjunction? Well, let's think about it. So that would be, it's necessary that P or Q implies that it's necessary that P or it's necessary that Q. So it's necessary that P or Q means that in all possible worlds, either P is true or Q is true. So you could have half the possible worlds where P is true, and in all those worlds, Q is false. And the other half of the possible worlds where Q is true, and in fact, P is false. In this scenario, the antecedent of our distributing necessity across disjunction is true, but the consequent, of course, is false, because P is not necessary, because P is only true in half the worlds, and Q is not necessary, because Q is only true in half the worlds. But together, either P or Q is necessary, because in all possible worlds, either P is true or Q is true. Hopefully that makes sense. Now, what about exporting possibility across conjunction? So that would be, it's possible that Q and it's possible that P implies that it's possible that P and Q. That means that it's possible that P in some possible world A. It's possible that Q in some possible world B. That doesn't imply that they're true in the same world, which is what the consequent has to be saying. The consequent is saying that they're in fact true in the same world, which isn't necessarily the case. Just because it's possible that P in one possible world and it's possible that Q in some other possible world, it doesn't mean that they're both possible in the same world, necessarily. So that one's going to be invalid. This only leaves us with exporting possibility across disjunction. And this one is going to be the last kind of iteration of Axiom K that we need to prove. So let's get started. This is going to look something like this. We're exporting possibility across disjunction. And it's going to be another that we can do quite quickly using transposition. So we'll universally instantiate modal distribution, our distributing necessity across conjunction, but we'll universally instantiate it once again with not P and not Q instead. We'll use De Morgan's law to pull out the negations and change those to disjunctions, which is what we're looking for in the end. We'll change our modal quantifiers to get possibilities instead of necessities and get rid of a number of those disjunctions, negations. And then we'll use transposition to switch them and end up with the exact axiom we were looking for. As with the previous proof, Once you have proved that you can distribute necessity across conjunction, you can easily show that you can export possibility across disjunction. However, with all of these, you will need Axiom K and the necessitation rule just to get started. Now, problem 7. Here is the translation. So, if you wanted to try just this translation after I translate it and just try it with the logic, here's where you want to start. So, it is obligatory that you believe that God exists. It's obligatory that you, or represent with a Y, believe that God exists, G. There exists no reason that justifies belief in God. It's not the case there exists some reason R such that R justifies G. Makes sense. For all P, if you know that P, that implies that there exists some reason R that justifies P. Or, if you know something, there is a reason that justifies your knowledge. Therefore, there is something that you are obligated to believe which you do not know. Alright? That's how I'm going to translate these premises. That seems to me to be the most sensible way to translate the premises. If you want to argue for a different translation, offer it in the comments below. What we're going to do now is we're going to move on to the proof of this one, and then we'll go back to the next translation, and back and forth, and so on. Okay? So, this proof is going to look like this. So, we have, there exists some P such that it's obligatory that you believe that P, and it's not the case that you know that P. We'll start with our premises that were just given to us. Now, the first thing we're going to do is universally instantiate premise 3 for that P to be G, the statement that God exists, because that's the statement we're using in premises 1 and 2. Then we'll use modus tollens to get, it's not the case that you know that God exists, because you need some reason to justify your knowledge that God exists, and based on our standard internalist definition of knowledge, hopefully that makes sense. Then we're going to conjoin 1 and 5 to get, it's obligatory that you believe that God exists, and it's not the case that you know that God exists with conjunction. And finally, using our existential generalization in premise 6, we'll get there exists some P such that it's obligatory that you believe that P, and it's not the case that you know that P is true, which is our conclusion. Hopefully pretty simple, basic introduction to give you some sense of how to start working with these different kinds of modal logics together. All right? We're only going more complicated from here. So, for all Muslims, it is obligatory, if you have not been on the Hajj in the past, that you go at some point in the future, and that you stone the devil when there. All Sunnis are Muslims. Rohan knows that Bill is a Sunni that has never been on the Hajj. Therefore, it is obligatory that Bill go on the Hajj at some point in the future. So, for all Muslims, if it's not the case in the past that you have been on the Hajj, so X is representing our Muslim. So if X is a Muslim, that implies that if it's not the case in the past that X has been on the Hajj, that implies that it's obligatory that at some point in the future, X goes on the Hajj and X stones the devil. For all X, X is a Sunni, implies that X is a Muslim. It's a basic translation of the universal affirmative. Then Rohan knows that Bill is a Sunni that has never been on the Hajj, so Rohan knows that Bill is an S, Bill is a Sunni, and it's not the case at some point in the past that Bill has been on the Hajj. Therefore, it's obligatory at some point in the future that Bill goes on the Hajj. For an explanation of why I've done obligatory and outside of our temporal quantifiers instead of inside those, instead of switched obligatory and future, watch my video on using obligation and time. I think it's called something like Are Obligations Eternal? It was one of the first videos that we looked at in this final 10 days of modal logic series. Check that one out. It should give you some information on the difference between those two ideas. All right, what we're going to do now is show the proof. So if you want to try the proof on your own with these translations, give it a try. If you have different translations, write them in the comments below and we'll take a look. So, these are our premises. This is our conclusion. Let's get started. So, anything that has knowledge in front of it, we can use the factivity axiom, or axiom T, to just turn it into a statement. And that's what we're going to do with premise 3. Then we'll simplify premise 4 down to Bill is a Sunni. We can universally instantiate premise 2 to be that if Bill is a Sunni, then Bill is a Muslim. We can conclude from 5, 6 modus ponens that Bill is Muslim. Pretty easy so far. Then we can go ahead and universally instantiate premise 8 to if Bill is a Muslim, then everything there. If he hasn't been on the Hajj in the past, that implies that it's obligatory that at some point in the future you go on the Hajj and stone the devil. Then with modus ponens, we can use 7 and 8 to get just, if it's not the case that Bill has been on the Hajj in the past, then it's obligatory that at some point in the future, Bill go on the Hajj and Bill stone the devil. From premise 4 simplification, we can get it's not the case that Bill's been on the Hajj in the past. Therefore, 9, 10 modus ponens we get it's obligatory that at some point in the future, Bill go on the Hajj and Bill stone the devil. Here's where things get a little tricky. You might want to just take that weak modal quantifier at some point in the future and distribute it across our HB and our DB. But that's not going to work. Or at least that's not exactly what our rule says. So we're going to be a little bit careful. We're going to do an assumed conditional proof and draw a line going down. We're going to assume that if F quantifies over HB and DB, and then use our modal distribution rule, because then we're definitely allowed, because we don't have that obligation on the outside of it to do that, and get this implication. Then we're going to use our necessitation rule to put obligation outside that again, and then Axiom K to distribute obligation across those. The important thing to note here is that if you don't have the necessitation rule for deontic logic, you wouldn't be able to do this, and it would be invalid for you to distribute that future quantifier across HB and DB. You wouldn't be allowed to. And if you didn't have Axiom K either for obligation, you wouldn't be allowed to. Those are the only ways to do it. So that's the reason we took those extra steps to do it, to show that you actually need all of those things. And if you didn't even have modal distribution, though that follows from the necessitation rule in Axiom K. Now we can use modus ponens with 11 and 16 to get it's obligatory that at some point in the future, Bill goes on the Hajj, and at some point in the future, Bill stones the devil. Now we can use our modal distribution to distribute the obligation, because there's nothing outside the obligation. That's just a standard taking FHB as P and FDB as Q. We can understand that in terms of modal distribution. We can clearly, easily distribute that, and then simplify that down to it's obligatory that at some point in the future, Bill goes on the Hajj. Hopefully all of that made sense, especially the pieces of why you can't just make the future go across HB and DP, because that would mean that you're assuming and forcibly assuming that Axiom K and necessitation rule are part of the system without having those forcibly assumed there. So it's a little sketchy territory. If you went through and proved all of this and then wanted to go back and do it over and over again, you maybe could use this as a precedent and use this as a rule to do it again. But for now, we want to be very explicit with how we're proving each of these proofs. Okay? Now, if you want to go back, if you've made that mistake in some of your past proofs on the other problems, I'd highly suggest you do that now. Okay? With that piece of information in hand, let's keep going. So our next translation is, murder is impermissible in all possible worlds. In all possible worlds, it is permissible to either be a vegetarian or commit murder. Therefore, in all possible worlds, it is permissible to be a vegetarian. This seems like a simple problem, but remembering what we just learned, it's actually going to be a bit more complicated. So, in all possible worlds, it's impermissible to murder. In all possible worlds, it's permissible to be a vegetarian or to murder. I'm using G for vegetarian instead of V because that might get confusing with our symbol for disjunction. Therefore, in all possible worlds, it's permissible to be a vegetarian. Right? So, here we go. Our original premises are, in all possible worlds, it's impermissible to murder, and in all possible worlds, it's permissible to be either vegetarian or commit murder. Therefore, in all possible worlds, it's permissible to be a vegetarian. We'll draw our line going down. We're going to start with an assumed conditional proof. And we'll basically show that within this, without including the necessity, because you want to distribute that permissibility to G and M and just include that necessity and ignore kind of that necessity there. But to be true to our rules and be very explicit, we're going to do a separate assumed conditional proof, then distribute our permissibility, then take it back out into an implication, then use the necessitation rule over the top of it to show that it's all necessary, and eventually use Axiom K to distribute that necessity. But we're going to do something else first. So, assume conditional proof, draw a line going down. We'll simplify that to it's impermissible that M, which deontic definitions can show it's the same as it's not the case that it's permissible that M, impermissibility being it's not the case that it's permissible. Note that this is going to look very much like what we did before, but just with another extra step. So we're going to have it's permissible at G or it's permissible at M. Therefore, it's permissible that G from 1011 disjunctive syllogism. Therefore, this long thing, so it's permissible that G or it's permissible that M, and it's impermissible that M implies that it's permissible that G from 7 through 12 conditional proof. The reason that we're doing these conditional proofs is so that we can use our necessitation rule. First, we're going to use exportation to get rid of that conjunction and turn it into an implication. Then we're going to use the necessitation rule to stick our necessary out front there. Then we will use Axiom K to distribute necessary across. Now, finally, we will take our premise 6, actually, not premise 5, and use Axiom K, not the necessitation rule. I apologize for that mistake. That should be premise 6, Axiom K, to distribute necessitation across there. Then we are going to use premise 2, premise 17, and modus ponens to get it's necessary that it's permissible that G or it's permissible that M. Then using 16 and 18, we can get it's necessary that it's impermissible that M implies that it's permissible that G. Axiom K this time will distribute our necessity. Note that we couldn't have done that earlier because it was in the confines of a larger statement. And then using 1 and 20, modus ponens will get it's necessary that it's permissible that G. All right. Finally, Fatu knows that she should have talked to her daughter about sex last week. So Fatu knows that at some point in the past, it was obligatory that she should talk to her daughter about sex. Okay? There exists some specific point in the past when she should have talked to her daughter about that. Once again, go to our obligations eternal looking at deontic and temporal logic if you want a better understanding of why we've put them in that order. Fatu knows that she has never talked to her daughter about sex before, so Fatu knows that it's not the case that she's talked to her daughter about sex. Fatu knows that, once again, for all P, for all possible propositions, if at some point in the past she was obligated to do P, and it's not the case that she did P at that point in the past, then at some point in the future she'll be obligated to do P. It's very important, the scopes of each of these temporal quantifiers. So the scope of the P only goes over obligation that P and not the case that P. And note that those are happening at the same time, at that same point in the past. Both, it was obligatory that P and she did not do that P. Whereas the future temporal quantifier is going over just the obligation, and the knowledge quantifier as well as the universal quantifier before all P are going over everything in the statement. Okay? Therefore, at some point in the future, Fatu's obligated to talk to her daughter about sex. Also, remember our bonus question related to this, which is to try to prove this with claiming that Fatu has logical omniscience, basically saying that you can use the necessitation rule for epistemic logic, and that our conclusion now is, instead of it's just at some point in the future obligatory that Fatu talk to her daughter about sex, but rather Fatu knows that at some point in the future it's obligatory that she talk to her daughter about sex. Note that that conclusion includes all of epistemic, temporal, and deontic logic. So, let's give it a try. We have premise 1. Fatu knows that at some point in the past it was obligatory to talk to her daughter about sex, and all of our rest of our premises. Here's our first conclusion that we're going to try to get to. It's going to take a little bit of work. So, first off, we're going to universally instantiate premise 3, because the only statement we're really talking about is talk to your daughter about sex, so S will go in for P. Then we'll go ahead and use the factivity axiom on all of these. Note that for the bonus question, you don't need premises 5, 6, and 7, so you can actually throw those out and not really need the factivity axiom. But for the original conclusion, you are going to need to use factivity. So remember that factivity is just axiom T for knowledge. Basically, we're dropping off the knows that, knows that, knows that criterion on all three of those statements. Then we're going to do an assume conditional proof. Draw a line going down for it's not the case that S and S, or it's not the case that it's obligatory that S. Get not S through simplification, get S, or it's not the case it's obligatory that S. Another, again through simplification, and then use disjunctive syllogism to get it's not the case it's obligatory that S. Those four premises via conditional proof show that S, not S, and S, or it's not obligatory that S imply it's not obligatory that S. Then we'll use exportation to change that conjunction to an implication. Then we'll use our necessitation rule to get it has always been the case that it's not the case that S implies that S, or it's not the case it's obligatory that S implies that it's not the case it's obligatory that S. Then we'll use Axiom K to distribute that strong operator to the two parts of our implication. Now, right now you might want to say, well, let's just use premise 6 and premise 15 to do a modus ponens, and then we can distribute using Axiom K as well. Again, you can do that if you want. The reason that I'm going to shy away from that right now is I'm going to do this such that you can also then go on to prove the bonus problem as well. That is a bit of a shortcut here, but that's not what we're going to do here. Now, we're going to draw a line going down and have an assumed conditional proof. So, we're going to assume that it has always been the case that this implication, and then use Axiom K to distribute that has always been the case, and the parentheses there correctly there. Now, that's a heck of a conditional proof we've just done. Basically, we've used our conditional proof to state explicitly that you can distribute it has always been the case, that strong temporal operator across an implication. That's what we're doing here. And you could also have done this by universally instantiating Axiom K. But, once again, I want to show a couple different ways to do these things. Then we'll use hypothetical syllogism to get a longer implication saying it has always been the case that not S implies that it has always been the case that S, or it's not the case it's obligatory that S implies that it has always been the case that it's not the case it's obligatory that S. Basically, just going back to our premise 15 and distributing the has always been the case across the two parts of that implication. All right, moving on. So, it has always been the case that not S implies that all of this stuff. That's from the previous page, hypothetical syllogism. Then we're going to use transposition on the second half of our implication, on the consequence of our implication. Then we'll use De Morgan's rule to change that disjunction into a conjunction. We'll use our change of temporal quantifier to get some pasts in there. Then we will use modus ponens finally with premise 6. This is going for just this solution, not the general solution. And premise 22, to get this, we'll use 7 and 23 modus ponens to get at some point in the past it was the case that it's not the case that S and it's obligatory that S, and then we can use 5 and 24 modus ponens to get at some point in the future it will be obligatory for Fatu to talk to her daughter about sex. Those last three premises are not needed for the bonus problem. So that was the normal problem conclusion. If you want to look at that and see if you can use the new way that I've done this to prove the bonus, give it a try right now and pause the video because we are going on to prove the bonus. The bonus is Fatu knows that at some point in the future it'll be obligatory for her to talk to her daughter about sex. So, jumping back to premise 22, we will use the necessitation rule and knowledge, remembering that to do this we have to assume that Fatu is logically omniscient, to put that KF at the beginning of that. Then we'll use Axiom K to distribute knowledge across those things. Once again, we're going to do this quick assume conditional proof trick to show that knowledge can distribute across all of that implication with Axiom K. Then we're going to create a very long implication from our conditional proof. Then we'll use hypothetical syllogism to shorten that down a little bit, and you should see that the two antecedents we have are statements we already have in the original premises, so we should quickly move to the proof of the last premise. So we will use modus ponens to shorten that down a little bit to 31, and then 132 to shorten it down even further. Note that this is exactly where we were with premise 24, but now it has the knowledge operator out front. Now we will use premise for Axiom K to distribute our knowledge operator across that, and finally use modus ponens to show that Fatu knows that at some point in the future it's obligatory that Fatu talk to her daughter about sex. Note that this final conclusion, as I said before, has epistemic, temporal, and deontic logic all in one. Okay, that was a lot of logic I just threw at you. There's probably some parentheses missing in there somewhere. Feel free to comb through it, see if you can do better than me, see if you can solve these problems in fewer premises than I did. Give it a try. Hopefully, if you have solved all of these correctly, I'm amazed, I'm impressed. You are a master modal logician. Even if you just solved a few of them, you are pretty darn good at modal logics. You've made it through possibly up to 200 videos on logic and modal logic. Congratulations, great job. Up next, series like this take time. It's a lot of work for me to produce a video every single day, even if it's only a 1.5 to a 3-minute video. So it's going to take some time before we do another one. There are, however, two possible topics that we could look at that I've been kind of going back and forth on of what I want to look at and what I think would be most useful for you to look at as the next step in logic. Both of these topics are very useful, but they're kind of taking us in different directions. Comment below, and there may be a card and a survey that I might try to put on that you can also comment with your choice of what you want your next 100 or Logic 301 short videos to be on. Either set theory, kind of taking us in the direction of logic and mathematics, or non-classical logic, a series I've been wanting to do for a while, talking about the different kinds of logic that don't fit the classical framework. All right, vote for your favorite topic for the next big, gigantic logic series. Thank you so much for watching all of these fantastic, you're fantastic subscribers. The videos, they're okay. Watch this video and more here at Carneades.org, and stay skeptical, everybody.